Dear students, today we'll see the part 4 on semiconductor electronics, in which we'll see some MCQs on digital electronics, that too on basic logic gates. So let's start with the questions. Question number 1, that is question number 61. Boolean algebra is essentially based on options are truth, logic, symbol, and numbers. Out of this, the a concept which is related is logic, because logic is one which will give whether it is true or false, true or false, whether it was yes or no, and then true or false, yes or no, then true and yes. This type of happening things can be taken as logic 1, and this kind of not happening things can be taken as logic 0. So this gives an idea of Boolean algebra. So it is a logical concept. So it is logic on which it is based. Then based on this 1 and 0 binary system, we can have the algebra of Boolean. So Boolean algebra can take place. So it is a logical system, either true or false, either happening or not happening, either yes or no, either high or low. So in that way, we can go with this logic, and that logic is the basis of Boolean algebra. So Boolean algebra is essentially based on logic. So option B is the right answer here. So you can see option B, that is logic, is the right answer. Then we'll go to the next question. The output of the OR gate is 1 if options are if both inputs are 0, if either or both inputs are 1, if both inputs are 1, only if both inputs are 1, or if either input is 0. Now, in this case, we have to remember the truth table for OR gate. So if you remember the truth table for OR gate, you can have, say, a two input OR gate. The inputs are A and B, and the output is Y, say. Okay, so if the input is 0, 0, what is the output? If the input is 0, 1, what is the output? If the input is 1, 0, what is the output? If the input is 1, 1, what is the output? Now, in this case, when the input is 0, 0 for OR gate, the output is 0. If the input is 0, 1, that is, if any one of the input is high, the output is high. So even here, when it is 1, 0, the output is high. When both the inputs are high, also the output is high. Okay. Now, this truth table relates to which statement? So statement A is if both inputs are 0, the output is high. No. If either or both inputs are 1, the output is high. This is true. So the statement B is very true with this truth table of OR gate. So then here the option B will be the right answer. If either or both inputs are high, logic 1, then the output of OR gate will become 1. So here you can see option B is the right answer. Then we'll go to the next question. Which of the following logic gates is a universal gate? Now, when we studied Boolean algebra, when we studied basic logic gates, we saw the basic logic gates which were named as NOT gate, AND gate, and OR gate. Okay. And then we also studied universal gates, that were the gates by taking those gates we can build any other gate. So those were called as universal gates, and what we studied in that was NOR gate and NAND gate. Okay, so NOR and NAND are the universal gates. So out of this option, it has been asked that which of the following logic gates is a universal gate. So OR is not a universal gate, NOT is not a universal gate, AND is not a universal gate, NOR is a universal gate. So option D is the right answer here. NOR is a universal gate. So here you can see option D, NOR is a universal gate. Then we'll go to the next question. The logic behind NOR gate is that it gives high output when both the inputs are low, low output when both the inputs are low, high output when both the inputs are high, none of the above. Now, if for this also we have to first remember what was our truth table for NOR gate. So for NOR gate, say the truth table, if you want to write, see if A and B are the inputs and Y is the output. Okay. So for OR gate, if you remember, then the complement of OR gate, we have to take it for NOR gate. So here, if the inputs are 0, 0, the output was 0 for OR gate. Okay, so output was 0 for OR gate, 0, 1, the output was 1 for OR gate. 1 0 the output of 1 for OR gate, and 1 1 the output was 1 for OR gate. Now complement of these outputs you will get the output of NOR gate. So when both the inputs are 0, the output will be 1. When any one or both the inputs are high, the output will be 0. Okay, 0. So this is what is the output of NOR gate. NOR gate. Now this, which statement in the given options relate to this output? So statement A says that high output when both the inputs are low, low output when both the inputs are low, high output when both the inputs are high, none of the above. Okay, so it is high output when both the inputs are low. So option A is the right answer. So here you can see when both the inputs are low, the output is high. Here you can see it is high. So high output when both the inputs are low is the right option. So option A is the right answer. So here you can see option A is the right answer. The logic behind NOR gate is that it gives high output when both the inputs are low. Then we'll go to the next question. How many NAND gates are used to form an AND gate? Okay. Now AND gate, we know the symbol was like this. This was AND gate. This is the two input and one output. So A, B, and Y. So AND gate, we know the truth table of AND gate also. It will give like say A and B are the inputs and Y is the output. 0 0 0 1 1 0 1 1. If any one of the input is low, the output is low, low, low. If both the inputs are high, the output is high. So this was your AND gate. Okay. Now NAND gate is just opposite of this. NAND gate will give the complement of this output. So Y for NAND gate will be 1 1 1 0. Okay. Now NAND gate looks like this. This is your NAND gate. NAND gate. Now A and B are the input. So the output here is A into B bar. Okay. Whereas the output of AND gate was A into B. Okay, now A into B bar should be again inverted. That means you can take one more NAND gate and you can short both the inputs, and then you can take the output so that the second NAND gate acts as a NOT gate. So this combination will give you the output as A into B. So this output will be same to this output. So to make a AND gate using NAND gates, we require two NAND gates. We require two NAND gates. So option B is the right answer here. Two NAND gates. So here you can see how many NAND gates are used to form an AND gate. It is two. Then we'll go to next question. The outputs of a NAND gate is 0 if both inputs are 0, if one input is 0 and the other input is 1, if both inputs are 1, if both inputs are 1 or one of the input is 1 and the other one is 0. Then again we have to come to the truth table of it. Okay, so basically we know the truth table of AND gate, and from AND gate we will develop a truth table for NAND gate. So if the inputs are A, B and output is Y, then for AND gate, both the inputs are high only, the output will be high. Now in that case, this output will be 0, 0, 0, and 1. Then for NAND gate, it will be just complement of this. So for NAND gate, the output will be 1, 1, 1, 0. Okay, so this is the output for NAND gate. Now which of the statement relates with this? The output of a NAND gate is 0 if both inputs are 1. If one input is 0 and the other input is 1, the first statement is if both inputs are 0. Second statement is if one input is 0 and the other input is 1. Third statement is if both inputs are 1. And the fourth statement is if both inputs are 1 or one of the inputs is 1 and the other input is 0. So the output of NAND gate is 0 when both inputs are high. Both inputs are 1. So here you can see when both inputs are 1, the output is 0 here. Okay, so this is the output of NAND gate. So here, out of these statements, option C will be the right answer. That is, if both inputs are 1. Then here we can see the outputs of a NAND gate is 0 if both inputs are 1. Then we'll go to next question. Identify the logic gate. So this symbol is for NOR gate. So here you can see this is the OR operation. This is the OR operation, and this is the bubble. This is the bubble. That is, the output will be complemented, the output will be inverted. So this combination becomes NOR option. NOR option. So here option D will be the right answer. That is, the logic gate which is shown above is a NOR gate. Here you can see option D, NOR gate is the right answer. Then we'll go to next question. The NOR gate is OR gate followed by dash gate. Options are AND gate, NAND gate, NOT gate, and none of the above. So we have seen the symbol of NOR gate. The symbol of NOR gate says that you are having a OR gate and then you are going to complement the output. You are going to complement the output by showing a bubble. That means you are having OR gate plus NOT gate. Okay, so this together will make a NOR gate. So it is OR gate which is followed by NOT gate. So option C is the right answer here, NOT gate. Then we'll go to the next question. So here you can see option C, that is NOT gate, is the right answer. The NOR gate is OR gate followed by NOT gate. Then we'll go to the next question. The NAND gate is AND gate followed by. So again here the same concept. If you have AND gate followed by a NOT gate, then you will get a NAND gate, which is shown like this. This is a NAND gate. So here you are having AND gate. This is AND concept, and this is NOT concept. Okay, so AND gate followed by a NOT gate will give you the NAND gate. So here in this question, the option A will be the right answer. That is NOT gate. So here you can see the NAND gate is AND gate followed by NOT gate. Then we'll go to the next question. In Boolean algebra, the bar sign indicates. The bar sign indicates means, say for example, if you're having A bar or B bar or C bar, if you are going to represent the variables like this, that means whatever is the value of A, the complement of that will be the value of bar A. Whatever is the value of B, the complement of that will be bar B. Whatever is the value of C, the complement of that will be bar C. That means if A was 1, if A is equal to 1, then A bar will be equal to 0. Okay. If B is equal to 0, then B bar will be equal to 1. Okay. That means you are going to complement the actual value. That is, the actual value is operated by NOT operation. In Boolean algebra, the bar sign indicates NOT operation. So option C will be the right answer here. So here you can see in Boolean algebra, the bar sign indicates NOT operation. Then we'll go to the next question. Which of the following is correct about logic gates? Logic gates have one or more input signals and only one output signal. Logic gate have only one input and output signal. Logic gates are analogous circuits. All logic gates have only one input and many output signals. So out of this, the first statement is true because logic gates can have two inputs, it can have three inputs, it can have four inputs. Okay, it can have one or more input, but there will be only one output. Output will be only one. It can have three input, it can have four inputs, but output will be only one. So the first statement, that is logic gates have one or more input signals and only one output signal, is the right answer. So here we can have an explanation. Logic gates are the basic building blocks of any digital system. Digital circuit with one or more input signals but only one output signal is known as a logic gate. All the other statements are not valid. So here only the valid statement is logic gates have one or more input signals and only one output signal. That is option A is the right answer. Then we'll go to the next question. The truth table shows both the input and output signals. So whenever we have a truth table, the concept of truth table, it is that it is a relationship between inputs and outputs. So if you are saying A and B are the inputs, okay, then we can have Y as the output. So this is for two input gate. So if we will take inputs as 0, 0, 0, 1, 1, 0, 1, 1, and depending upon which operation we are going to decide what will be the output here. This is the output. That means it is a relationship which shows both input and output. So this statement is true. This statement is true. The truth table shows both the input and output signals. It is a true statement. So option A is the right answer here. So here, yes, this is a true statement. The truth table is a table that shows all possible input combinations and the corresponding output combinations for a particular logic gate. These are used in connection with Boolean algebra, Boolean functions, and propositional calculus. So here you can see option A, that is a true, is the right answer. Then we'll go to the next question. Which gate will a NAND gate be equivalent to when two input of NAND gates are shorted? So if you're having a NAND gate, okay, so if you draw a NAND gate and it is a two input NAND gate, if the two inputs are shorted, if the two inputs are shorted, that means you will have only one input here and one output here. So here it is complemented also. Okay, and these two inputs will have the NAND function. So if both the inputs are same, say for example, if both the inputs are 1, 1, say 1, 1, the output will be 1, and here after inverting, the output will be 0. If this input is 0, similarly 0 into 0, 0, 0, and if it is knotted, it is 1. That means this is giving a function of NOT gate. This is giving a function of NOT gate. So which gate will a NAND gate be equivalent to when two inputs of a NAND gate are shorted? Then it is NOT gate. So option D will be the right answer. So here you can see when two inputs of a NAND gate are shorted, then the Boolean expression, it becomes y is equal to not a into a, that is not a, therefore it is NAND gate will be equivalent to the NOT gate. So here option D will be the right answer, NOT gate. Then we'll go to next question, question number 74. What should be done to obtain an OR gate from a NAND? We need only three NAND gates. We need two NOT gates obtained from NAND gates and one NAND gate. We need three NOT gates obtained from NAND gate and three NAND gates. We need two NAND gates and four AND gates obtained from NAND gates. So which of the combination is correct for this question? What should be done to obtain an OR gate from a NAND? So here you can see the explanation. We need a OR gate. Now OR gate is nothing but y is equal to a plus b, that is a ORing b, from NAND gate, where NAND gate's function is y is equal to a into b bar. This will be the function of NAND gate. So if you take this NAND gate a and b, this is the output y. So y will be nothing but a into b bar. Okay. Now if you take one more NAND gate, then you will get this as a into b bar and bar. Okay. Now here a into b bar bar will be nothing but a bar bar plus b bar bar, which will be nothing but a plus b. Okay. Now using this formula of Boolean identity, you get y is equal to a plus b, that is OR gate. Since not a is equal to a and not b is equal to b, therefore to obtain a OR gate from a NAND gate, we need two NOT gates obtained from NAND gate and one NAND gate. So we require two NOT gates obtained from NAND gate and one NAND gate. So here option B will be the right answer. What should be done to obtain an OR gate from NAND gate? We need two NOT gates obtained from NAND gate and one NAND gate. Option B will be the right answer. So then we'll go to the next question. The following truth table corresponds to the logic gate. So here, if you see this truth table, if both the inputs are 0, 0, the output is 0. If inputs are 0, 1, the output is 1. If inputs are 1, 1, the output is 1. If input are 1, 0, the output is 1. Okay. So here, if any one of the input or both the inputs are high, the output is high. That means this is a truth table for OR gate. So here the truth table corresponds to which gate? So option B is the right answer here, OR gate. So here you can see option B is the right answer, that is OR gate. Let's go to the next question. Next question is number 76. Which logic gate is represented by the following combination of logic gates? So here in the diagram, there is a representation of a combination of gates, and we will see what expression we are going to get at the output. So here the input A is given. So here you can see input A is given. The output of this NOT gate will be A bar. And here input B is given. Output of this NOT gate will be B bar. And here you are having a OR gate. So here the output will be A bar plus B bar. Okay. Now here A bar plus B bar is nothing but, it can also be written as AB the whole bar according to our De Morgan's theorem. So here AB the whole bar is nothing but is the output of NAND gate. This is output of NAND gate. NAND gate. So here option B will be the right answer, NAND gate. The above circuit represents NAND gate. So here you can see option B is the right answer here, NAND gate. Then we'll go to the next question. The logical states are categorized into how many groups? One group, two group, three group, or four group. So here the right answer for this is of three groups. The logical gates are categorized into three groups. So option C will be the right answer here. The logical gates are categorized into three groups. They are number one, basic gates group. Number two, a universal gates group. Number three, arithmetic gates group. So there are three groups in which logical gates can be categorized. So here you can see option C is the right answer, three groups. Then we'll go to the next question. How many AND gates are required to realize the function y is equal to CD plus EF plus G? So here we see the output y is equal to CD plus EF plus G. And the question is asked, how many AND gates are required? So one AND gate is required for this product and another AND gate is required for this product. So we require one AND gate here, one AND gate here. So totally 1 plus 1 is equal to 2 AND gates are required. 2 AND gates are required for this expression to be realized using logical gates. So here option D will be the right answer, 2 AND gates. So here to realize y is equal to CD plus EF plus G, two AND gates are required and two OR gates are required. So the AND gates requirement is 2. So here option D will be the right answer. Two AND gates are required. Then we'll go to the next question. The output Y of the logic circuit given below is what? Okay. So here you can see this input here is X bar. So X bar will be the input as one of the input for this XOR gate. This is XOR gate. And then X bar is complemented with a NOT gate. It is inverted. And here you get X as another input. Okay. So X and X bar are the two inputs. So if X is equal to 0, X bar is equal to 1. And if X is equal to 1, X bar is equal to 0. So this is the values of X and X bar. So both the inputs will be different. If one is 1, then the other will be logic 0. If one is logic 0, then the other will be logic 1. When both the inputs are different, the output of XOR gate is logical 1. The output of XOR gate is logical 1. So here, the output Y for X bar XOR X is equal to logical 1. Okay, so here option A will be the right answer. That is logic 1. So here you can see option A is the right answer. That is logic 1. Then we'll go to the next question. The output of logic circuit given below represents which gate? So here the logic circuit, if you analyze, so here you can see the first input here is A and the second input is B. So A after this NOR gate will become A bar and B after this NOR gate will become B bar. Then here another NOR gate is used. So here output will be A bar plus B bar the whole bar. And then here again it is inverted and here you will get the output A bar plus B bar and one more bar. So those both bars will get cancelled and what we will get is A bar plus B bar, and A bar plus B bar is nothing but A into B whole bar. A into B whole bar, and this is nothing but the output of a NAND gate. The output of a NAND gate. So here option D will be the right answer, that is NAND gate. So here you can see the output of the logic circuit given below represents which gate? It is NAND gate. It represents NAND gate is the answer. Thank you, students.